We've already seen that a charged particle moving through an electric field will experience a force. If this is a positively charged particle, it experiences a downward force, and therefore the path that it follows will be that of a parabola, just like a projectile in projectile motion last year in Physics 20. We know that a charged particle moving through a magnetic field will also experience a force. But what's the shape of the path in that case? Let's take a look closely at that. Let's say we've got a magnetic field pointing into the page here. Let's make it a negatively charged particle entering that uniform magnetic field moving to the right. We know that it's going to experience a force, and we're going to find the direction of that force by the hand rule for deflection, left-hand rule. Let's say thumb in the direction of the particle, which is to the left side of the page, the right side of the page, fingers in the direction of the field, which is into the page, palm points downward, so the magnetic force ends up being downward like this. Now, as a result of that negatively charged particle is going to change direction. It's going to go somewhere in between the way that it was moving and the direction of the force that's acting on it. So it's going to end up going somewhere down here. Now, instead of moving to the right, it's moving diagonally downwards. Let's look at the direction of the force now. Thumb in the direction of the particle, which is down and to the right, fingers in the field, which is still into the page. The palm now is going to point diagonally down and to the left. That's the direction of the magnetic force this time. Where is this particle going to go as a result of its inertia, which was down and to the right, and its magnetic force, which is down and to the left? Well, now it's going to end up going somewhere in between, down like this. Direction of the force now, thumb downwards, fingers into the page, palm points to the left. The direction of the magnetic force is to the left. Now where is it going to go? It's going to go somewhere over here, somewhere in between, right? Thumb down and to the right, down and to the left, fingers into the page, palm is going to point up and to the left. The magnetic force is this way. What do we notice about this? Well, this negatively charged particle experiences a magnetic force in every single case pointed to the same place. That would be the center of a circle. This charged particle doesn't follow a parabolic path like it would in an electric field. Rather, it follows a circular path in a magnetic field. And that's going to be the case always. Yesterday, we learned about charged particles in magnetic fields, and we learned to calculate that force. We didn't learn about the shape of the path that it takes, but the shape of the path would be a circle, even in yesterday's questions when we didn't need to know that. What we learned yesterday to describe that magnetic force is still applicable, still valid. F is equal to QVB, as long as the charged particle is moving perpendicular to the magnetic field. But because we now know this charged particle is moving in a circle, this equation from Physics 20 is also applicable, the centripetal force equation. The magnetic force causes this particle to go in a circle. The magnetic force provides a centripetal force. So now we can do this like we would have did yesterday, but we can also do this. Fc is equal to mv squared over r, or we could set those equal to each other and say Fc is equal to Fm. Generally, if a question talks about the radius of the path of the particle, you're probably going to use this last one. If it doesn't, you're probably going to use this one. Just keep in mind for all of these questions now where a charged particle is in a magnetic field, you can use any of the three equations depending upon the givens that you have. Let's take a look at an example that you have on the handout that I gave you yesterday. Example number 3, it says an electron, which is a negative particle, let's draw attention to that so we don't forget to make it negative, is moving with a speed of 4 times 10 to the 5 meters per second to the right through a magnetic field of magnitude 2.5 times 10 to the negative 2 Tesla directed into the page. Look, we got a particle traveling to the right, we got a magnetic field into the page, they're perpendicular. So everything we learned yesterday, the hand rule for deflection, the equation F is equal to QVB, the new equation that we just learned, Fc is equal to mv squared over r, they're all applicable. We want to find the radius of the path of the electron and which way it's going to bend. Let's write down some givens here. We know that the speed of this particle is 4.00 times 10 to the 5 meters per second. We know that the magnetic field strength is 2.50 times 10 to the negative 2 Tesla. We're looking for the radius of the path. Remember I said just a few minutes ago, if you're looking for radius, although F is equal to QVB is valid, so is mv squared over r, odds are what you're going to end up doing is the combination of the two, FC equals FM. So let's try that first. FC equals FM. So replace FC with mv squared over r, and let's replace FM with QVB. Let's cancel out one of the V's. V squared on the left side, V on the right side. One of the V's cancels out on both sides. And let's solve for R here. Now, to get that R by itself, we're going to take it up by multiplying, and then we're going to have to take the QB down by dividing. So we end up getting MV over QB equals R, the radius of the path of this electron. Let's sub in our numbers here. We got a mass of 9.11 times 10 to the minus 31 kilograms. We got a speed of 4.00 times 10 to the 5 meters per second. Divided by the charge of the electron, which is 1.60 times 10 to the minus 19 coulombs. Multiplied by the magnetic field strength, which is 2.50 times 10 to the negative 2 Tesla. Do the math there. Should work out to be 9.11 times 10 to the minus 5 meters. Now, which way does it bend? Up or down? We're going to say thumb goes in the direction of the particle, which is to the right. Fingers go in the direction of the field, which is into the page. Your palm will automatically point downwards toward the bottom of the page. Remember, your frame of reference is the page here, not north, south, east, west. So let's not just say down. Let's say it's toward the bottom of the page. All right, got a few questions for you to work on worksheet number 12, questions 1 to 5. I'm going to give you a little hint for question number 5. It asks you to compare the radius of the path of an alpha particle moving through the same magnetic field as an electron. When you want to compare two things, you divide. So we're going to say the radius of the path of the electron divided by the radius of the path of the alpha particle. Okay, whenever you see the word compare, think divide. Compare or ratio, think divide. All right, let's give those 5 questions a try, see what you can do.